Okay, thank you. So my name is Alena Kharissova. I'm from Mexico, from Universidad Autónoma de Nuevo Leon. I'll share my poster work, which is called Synthesis of Titanium Dioxide Sensitized with Thin Sulfide Quantum Dots for Application in Photovoltaic Devices and Solar Paints. So just as a quick introduction, the global electricity generation was increased significantly over the last decades. So in the 90s, the generation was 12,000 terawatt hour, and it increased to 27,000 terawatt hour in 2020. So currently, around the 25% of the generated electricity is made from renewable sources, and also only 2.4% of this is solar energy. Most of the scientific research and investments are done to this specific technology. Something important to mention is that when we need to improve the photovoltaic technology, it's important not only to consider to improve the efficiency, but also to solve two of the greatest environmental impact problems of the solar cells. One is the high production energy, because we need temperatures usually of about 1,000 Celsius, which is a very high carbon intensive process, and also the toxic chemical substances that we use in the solar cell production, because these can leach into the earth after the end of life and cause more harm to the soil, such as cause soil eutrophication. And this is why a sustainable production method is proposed into in this work. So there are generally three generations of solar cells. The amorphous and monocrystalline silicon cells are the most common ones, the ones that are commercially available. The second generation cell are thin technology films, and the third generations are the emerging technologies such as quantum dot sensitized solar cells, which I will be using in my work. And this is the working principle of quantum dot sensitized solar cells. So usually you have the semiconductor material, it receives light from a certain wavelength, and then electrons pass from the valence band to the conduction band, and the holes pass through the electrolyte through the redox cycle. And this creates an electrical current. So as I said, quantum dot sensitized solar cell material was developed in form of a paste at room temperature without the use of heat, using pseudo-solar technique and a very energy efficient method, which is ultrasonic bath. Here you can see the four main sample concentrations that were done. They were using the following reactive. As you can see, it's sulfide chloride, sodium sulfide, titanium dioxide, and these were the three main reactives that were used to obtain titanium dioxide with thin sulfide decoration. And some additives were used as well, such as polyethylene glycol, hydroxyethyl cellulose, and acetylacetone, because they were thought that they will increase the stability of the size of the quantum dot. This is the process of what was done. The synthesis methodology to obtain the quantum dot thin sulfide on titanium dioxide was the following. So we had anatase phase of titanium dioxide that was added to sulfide chloride, which was dissolved in distilled water and underwent an ultrasonic bath at room temperature from 1 to 2 minutes. Then the solid and the liquid part were separated through centrifugation process. The solid part was collected, which was the part with titanium dioxide, and the liquid part was removed. Afterwards, the collected titanium dioxide was then added to sodium sulfide, which is the second. That's the second. Here you can see, Same process was done, ultrasonic bath for 1 to 2 minutes, then centrifugation to remove the liquid part, the water part. And as a third step, it was washed with distilled water to avoid ions from the previous unreacted material to react with the next step of sulfide chloride, because it can react and form unwanted salts that we wanted to avoid in this part. So the whole process was repeated for 7 cycles and then dried at 40 degrees Celsius for 1 hour. And then the characterization process was done to the powder. These are some of the results that I wanted to share. Here we can see the transmission electron microscopy characterization that was done to the 4 samples. Titanium dioxide crystals of Anata's phase are observed with quantum dots. Especially well can be observed the quantum dots in sample 4. I think it was taking most of the next picture. So this is from sample 4. We analyze the interplanar distances of thin sulfide in sample 4 from the TEM image. And we can see that the distances correspond to orthorhombic thin sulfide peaks. Also from TEM, we could analyze the size of the quantum dots, and the size were observed varied from 2 nanometers to 20 nanometers, being the average size of all the 4 samples around 13 nanometers. Also, an energy dispersive X-ray spectroscopy, EDS, was done when doing TEM microscopy. And here's an example of the EDS of a selected region in one of the samples, and the percent of elements that we obtained. And we could see that we have titanium dioxide and tin sulfide elements as well. When doing the EDS in the TEM, there was also another qualitative verification. We can see also the different elements that we had, being titanium dioxide and tin sulfide also present. Being tin sulfide, the quantum dots in much less amount, of course, than the titanium dioxide. Another way to prove that the quantum dots were present in the material was the qualitative fluorescent test, which was carried out with a wavelength of 395 nanometers, and the light source, it was only a light source of UV that was irradiated towards the samples. And we could see there was a violet coloration observed in the 4 samples, something characteristic for quantum dots of a very small size. Also, X-ray was done to the samples. In X-ray results, which you can see in the figure in the left, we can see peaks referring to titanium dioxide only, no tin sulfide, because the amount of tin sulfide quantum dots was very low, and the sensitivity of X-ray does not identify this material. So we only have titanium dioxide in X-rays, but hence we did Raman spectroscopy because it has more sensitivity, and in Raman we could observe peaks of orthorhombic thin sulfide crystals. The peaks were 24, 64, 98, and 304, and the rest of the peaks belong to titanium dioxide. Also, UV characterization was done in order to find out the band gap of each of the samples. The band gap, as you may know, is the energy that we need from the valence band electrons to transition to the conduction band, having some incident radiation. And in the graph, we can see the band gap that's obtained from the energy and the covariant move function of energy, and the tangent of the inflection point in this material is the band gap of it. So in our case, we could see that for the most concentrated sample, which was sample 2, we had 2.74 electron volts, and for the rest of the sample was between 295 and 3.1 electron volts. And given that the quantum dots of tin sulfide in the literature by themselves have a band gap of 1.3 electron volts, and the anatase phase of titanium dioxide has 3.35 electron volts, it was expected that the band gap will be decreased with higher concentration of regions. So it was something new that we saw, that the higher the concentration of the regions, the lower the band gap. And the next pending characterization is the intensity current test. This is to get to know the efficiency of the photovoltaic material. For this, the samples were mixed with the polyethylene glycol, hydroxyethyl cellulose, and acetylacetone in order to form a paste, because initially they were in powder form. And then thin films of this paste were applied through, in FTO glass through Dr. Blade technique. You can see the samples already prepared. This is how this process will look like. The electrical conductivity tests will be done as you can see in FTO glass as electrode, and copper sulfide as counter electrode. And as a general summary, so one way to revolutionize solar energy production is to reduce the complexity of the manufacturing process, and the possibility to apply this kind of paste in any shape and any surface. And in this work, we used pseudo-scalar technique to develop quantum dots on titanium dioxide, and we successfully developed quantum dots on titanium dioxide using simple wet chemical modification of pseudo-scalar using 7 cycles of ultrasonic bath in aqueous solution of chlorine sulfide and sodium. And the samples were that we obtained had 13 nanometers. That was confirmed by using ADS, X-ray, and Raman spectroscopy. And the band gap that we found of the material was between 2.74 to 3.11 electron volts, being lower band gap when more concentration of reactives was used. And the next step will be to test the photocurrent density of this material to determine the efficiency of the solar paste, which is expected to be between 1 and 5%. And these are the references that I used. And please let me know if you have any questions.